As a fundamental principle in physics, vacuum decay is actually closely related to the lowest energy level steady state. In a system, energy always spontaneously moves towards the lowest energy level. For example, a ball on a mountaintop will roll down the slope with a gentle push. This is a typical process of falling to a lower energy state. In our universe, it is filled with various invisible fields, including gravitational fields, electromagnetic fields, quantum fields, etc. The most crucial among them is the Higgs field. The Higgs boson gives mass to all particles through the Higgs field and is one of the fundamental fields in the universe. However, the current standard cosmological model is actually in a metastable state of the Higgs field. In other words, our universe might be like a ball located on a mountaintop or halfway down the slope. It may rapidly fall to a lower energy level due to a tiny disturbance at any time. Physicists refer to this unstable state of the universe as a false vacuum. The stable universe we see now might just be a brief stage in the dynamic balance of the universe. Theoretically, vacuum decay could already be happening now and spreading through the universe at the speed of light, but we would never be able to detect it in advance. Another key question is, how much energy release is required to trigger vacuum decay? Liu Cixin once envisioned in The Village Teacher a collider encircling the Earth's equator, with energy comparable to the Big Bang, capable of instantly triggering vacuum decay. To prevent this disaster, an alien civilization came to Earth and stopped the operation of this collider. But in the real world, the collider with the highest energy density is the European Large Hadron Collider. Although it can accelerate particles to speeds approaching light, its energy density is still far from that of the instant of the Big Bang. Let alone recreating the Big Bang, it cannot even generate a black hole. Furthermore, the energy densities of other astronomical phenomena in the universe are also insufficient to push the entire universe out of the false vacuum state and trigger vacuum decay. Therefore, from this perspective, our universe is currently in a relatively safe state. But the problem is, the universe is governed by quantum mechanics. In the microscopic world that we cannot see, quantum fluctuations occur all the time. The stable state of the entire universe is essentially also a quantum state, full of uncertainty. This means that any region of the universe could become the starting point of vacuum decay. This further leads to changes in the overall state of the entire universe. If vacuum decay occurs within the solar system, Earth would undoubtedly turn into fundamental particles. All physical laws within the scope of the solar system would also completely disappear, and this new vacuum would continue to expand outward at the speed of light. If you were to witness the moment of vacuum decay, you would vanish instantly, without any pain. As for vacuum decay occurring in other regions of the universe, it might take tens of millions, or even tens of billions of years for its effects to reach Earth, which is far from enough to affect our current lives. Even possibly before the vacuum decay reaches the Earth, human civilization might have already disappeared from the universe. Is faster-than-light travel possible? If you shine a laser at the moon, even a slight flick of your wrist will cause the light spot on the moon 380,000 kilometers away to move. This kind of superluminal motion is called phase velocity, a non-material velocity phenomenon. Since it does not transmit information, it does not violate Einstein's theory of relativity. What we really need is actually a faster-than-light spacecraft, like the Enterprise in Star Trek. It uses a warp drive, encapsulating the spacecraft in a special space bubble to circumvent the speed of light limit and travel faster than light through the universe. However, current theory does not support this kind of technology because Einstein's theory of relativity only allows objects to approach the speed of light infinitely, but not to reach or exceed it. You might think the speed of light is fast enough. It can circle the Earth 7.5 times per second, but on a cosmic scale, this is like a snail crawling. The most distant galaxy currently known from Earth, GNZ 11, is located 13.2 billion light years away, meaning what we see is how it looked 13.2 billion years ago. Even more astonishingly, because the universe is expanding faster than light, the actual current distance of GNZ 11 from us is already 18 billion light years, and it will continue to accelerate away from Earth in the future. In fact, 13.82 billion years after the Big Bang, 98% of the galaxies within the observable universe have already lost contact with Earth. What we see now is only how they looked billions of years ago. In the future, As the universe expands faster than light, the stars in Earth's night sky will successively recede beyond Earth's light cone. One day, when we look up at the stars again, except for a few planets within the solar system, we will not see any other stars. However, although Einstein forbade any object from exceeding the speed of light, he left us a spatial tunnel connecting distant corners of the universe, the Einstein-Rosen bridge, also known as a wormhole. According to the latest research, it is entirely possible for wormholes to enable travel from one region of the universe to another at speeds far exceeding light. If, besides the three spatial dimensions and one time dimension, there exists a fifth dimension with highly concentrated quantum fluctuations, then in the future, once human civilization develops to a sufficiently advanced stage, we might be able to use wormholes like we use subways today. However, scientists have never detected the existence of a fifth dimension. Even if it does exist, it would require exotic matter, or negative energy, to maintain the size and stability of the wormhole. Otherwise, passing through an unstable wormhole would be like going through a meat grinder. All particles would be torn apart and unable to reassemble. What's more troublesome is that wormholes cannot avoid the time dilation effect. When you travel through a wormhole at superluminal speeds, time outside the wormhole still passes normally. This means that even if you only spend 1 second in the wormhole, thousands of years may have passed outside. Therefore, when you return from the wormhole, the world would have changed beyond recognition. At the U.S. congressional hearing in July 2023, Air Force officers and former intelligence officials publicly claimed that the previously photographed UFOs could be faster-than-light spacecraft of alien civilizations, arriving at Earth from several light years away. However, scientists do not agree with this statement because any faster-than-light motion would leave obvious traces in the universe, and no such traces have been observed so far. Overall, although faster-than-light technology is still far from us, with future in-depth research on general relativity, we will eventually master the nature of space and gravity and develop brand new aerospace propulsion technology. How big is the real universe? The observable universe, often mentioned by astronomers, has a diameter of about 93 billion light-years, but this is only a small part of the real universe. It is a special region formed because the light from galaxies beyond this distance cannot reach Earth. Within the observable universe, the Hubble telescope has discovered 2 trillion galaxies, 98% of which have permanently lost contact with Earth due to the universe's faster-than-light expansion. The light they emit, while moving away from Earth faster than light, can never reach Earth. Therefore, all the cosmic galaxies we see now are their past selves. Astronomers estimate that, according to the current rate of cosmic expansion, at a distance of 14.6 billion light-years from Earth, the speed of cosmic expansion just exceeds the speed of light. That is to say, once a galaxy crosses this boundary, it no longer has a causal relationship with Earth. The scale of the real universe is at least 250 times that of the observable universe. This data is based on actual measurements. Although we cannot directly measure the extent of the universe through the cosmic microwave background radiation map, astronomers can obtain the distribution density of galaxies in different directions of the universe, thus outlining part of the outline of the real universe. By observing the curvature of this region, we have currently confirmed that the shape of the universe is an infinitely extended flat structure, but it has a slight curvature. This means the universe could be closed. On this almost imperceptible curvature, astronomers have discovered, as long as the scope of the observable universe is expanded by 250 times, its curvature will close into a sphere. And this sphere is the size of the real universe. This kind of closed four-dimensional hypersphere universe was also predicted by Einstein in the general theory of relativity. He believed that, in such a universe, a person could even see the back of their own head, because light travels along geodesics in a vacuum, and the existence of curvature means the universe is closed. So the path of light propagation will also close accordingly. This causes the light emitted from the back of the head, after traveling through the universe for hundreds of millions of years, to return to the origin from the opposite direction, thus allowing one to see the back of their own head. Similarly, in such a universe, flying a light-speed spacecraft consistently in one direction, just like sailing around the world on Earth, would eventually return to the starting point. This means we may never truly leave the universe. As for the multiverse and parallel universe theories, there is currently no evidence to prove their reality. However, the speed of light may be just a layer of window paper, not an unbreakable iron law. The scientific community speculates that, if humans can achieve faster-than-light travel, they might break through the boundaries of this closed universe, just like reaching the first cosmic velocity on Earth allows entry into space. On a cosmic scale, faster-than-light travel might open up new directions, allowing us to fly outside the universe. According to the bubble universe model, our universe is just one of many universe bubbles in a higher dimensional space, each containing completely different physical laws. Therefore, even if we can fly out of our own universe, entering other universes is not easy. Different physical laws would likely cause matter from Earth to disintegrate instantly. Of course, there is another possibility. Our universe itself is virtual. Many figures in the tech field, including Musk, have proposed similar views. Perhaps in the vast real space, humans are merely NPCs, non-player characters, in some enormous system.